All right, guys. I'm sorry that the video from last lecture couldn't be recorded. We just got 10 minutes of that, which is mostly the part of the review, so all the part of deviated wellbores is not there. But I recommend that you read the notes. The notes say almost everything of what I explained in class. So let's see. Today I'd like to finish the topic of wellbore stability, and then we'll move to the homework, and then we'll move to reviewing all the exams, all right? So let me find that. So it's homework. And this is the last thing that we saw that, let me come back one more page. So there are 4 very important factors to take into consideration for wellbore stability other than the ones that we have already seen about tensile fractures, shear fractures, and wellbore deviation. In addition to that, for the mechanics of the wellbore, it's also very important that you consider temperature. Basically, lowering the temperature in the wellbore is going to promote tensile fractures, and that could not be good. It might be good for reducing likelihood of breakouts, because breakouts are due to compression. But if that's too much, that can lead to tensile fractures. The second factor that we saw is the instability of shales to fresh water. If you expose shales to fresh water, they're going to swell, they're going to get weaker, and if that's the rock that's making out the walls of your wellbore, that's not going to be good, because that's going to lead to more breakouts. And the solutions for that, as we said before, are either increasing the salinity of the mud, which this costs money, right? So you don't want to do this unless you know that you have instability problems. So, but that's a possible solution. Increase the salinity of the drilling mud, use an oil-based mud, or do underbalance drilling. All those 3 are possible solutions for avoiding shale instability. Sands, carbonates, formations like that usually do not have these kind of problems because they do not have abundant clay in the rock. It may have a little bit of clay, but if it's not a major component in the rock, that's not going to be an issue. There is something very similar that happens with water flooding. If you do water floodings with low salinity water, the clays inside sandstone also can swell and can clog the pores and lower the permeability. It's exactly the same phenomenon, but these are 2 different applications. This is the one for drilling. And third, it's also very important that you consider that your mud cake is actually doing what you expect that it will do. As we have seen before, the effect of the mud cake is to, if you have a formation which is a porous medium, the effect of the mud cake is to form a layer where drilling mud filtrates, and you may have some small particles that get into the formation. But the objective of that is to create a very sharp gradient between the pore pressure in the formation, PP, and the wellbore pressure in the drilling mud. It is not guaranteed that you are going to obtain something like this in practice. In fact, if you don't design well the particulates inside the drilling mat, you're not going to have a mud cake. And that depends on the rock properties as well. Even if you design it well, over time, if you spend a lot of time drilling a section, you could get into a situation in which the same rock now, especially if the particulates in the mud cake are not very well designed, they start to filtrate more and more inside the rock, and you will lose that low permeability barrier that you had before. If you lose that low permeability barrier, what do you think is going to happen with the gradient of pressure? So if this, let's say that we still continue with the same pressure in the wellbore, PW, PP is somewhere over here. And this is going to be as time passes. If you lose this mud cake, if you lose that low permeability barrier, now your gradient is not going to be as sharp as before, and you might have a more gradual transition between the wellbore pressure and the pore pressure. And because of that, now at the wall of the wellbore, you cannot consider that your effective stress was, your support was this much. So for example, before, right at this point, more or less at the wall of the wellbore, your effective stress radial support, and that's what you put in your equations as sigma RR, is PW minus PP. That's what we have been using. And that assumes kind of a perfect mud cake, which is very sharp at the interface. But look, now if at that same point you have much less of a difference, now you're going to have a smaller effective stress radial support. And if you have a smaller effective stress radial support, that's going to impact directly the strength of the rock, because as we know, the shear strength of the rock is proportional to the minimum principal stress. So the lower this one is, the weaker the rock is going to be. And if the rock gets weaker, that also is going to mean that you're going to have more likelihood of shear fractures and for breakouts. So it happens sometimes in practice that you may be drilling a wellbore and everything is okay, but if you wait too much in order to case that wellbore, you may expect to see failure after a few hours or a few days if you don't do this quickly enough, and you let some of that small particles in the mud cake to get into the rock. Usually this is a problem with high permeability rocks. If it's low permeability rock, it's very unlikely that those mud particles are going to get into the formation. But it is very important that you remember that in most of our equations we have considered in a perfect mud cake, and that's not always the case. And that's something that you have to consider in your design of the drilling mat to make sure that the equations that you apply are accurate for your particular application. So let me ask just one more thing here. So the implication of this is that breakouts will appear after some time. or if you already have breakouts, those breakout angles are going to increase. Okay, and now let's take a look at the last factor to take into consideration, fourth of the most important ones. And that one is something that we saw before, but we didn't talk much about the applications. And this is strength anisotropy. That means that the strength of the rock is different in different directions. If you were to run a triaxial test or an unconfined compression test as the ones that you have already done in the laboratory, talking about the laboratory, there is a scheduled laboratory, I think, for next week, but we're going to do that laboratory in class, okay? So no need to show up Monday 2 p.m. or Tuesday 2 p.m. I'm going to bring that small load frame over here, and we'll do it in class all together, all right? Okay, I'll send an email about that. But, okay, so we were here, strength anisotropy. Rocks, as we know, they are not isotropic. Usually, when you go into a sedimentary rock, you have layers because this is the process of sedimentation. And it's not the same if you take a rock in this direction or if you were to take a rock at an angle. Many times, not always, but many times, these planes are planes of weakness. So if I were to test, for example, rock number 1, I may get something like this. But if I were to test rock number 2, what do you think I will get if I assume that these are planes of weakness? Let's go to the extreme case scenario where those are just open fractures. Do you think I would be able to run a test like this if I don't have any confining pressure? So if I don't have any confining pressure and there is, those planes are not cemented, anything, they're just going to slide one next to each other, right? You may have some strength if you have a normal stress applying on it, but otherwise you will have very little. So let's consider they are just poorly cemented, but anyways, those are going to be much weaker than the one in this direction. Why? Because if you were to create a fracture, a shear fracture into this rock, the shear fracture will have to cut through some of those intact rock layers. But if you were to run a test into this rock with already some weak planes in there, do you see that those weak planes now align with the expected orientation of the shear fractures? So it will just break like that. And if we're saying that those planes are very weak, then the overall strength of the rock is going to be very weak. It is exactly the same if we run, so this one was an unconfined compression test. But it will be exactly the same if we run, for example, a tensile strength test. It's not the same to run a tensile strength test on a rock like this, where you would expect that your fracture, how is the fracture going to happen in this test? In which direction? Do you think it's going to be like this or like that? The first one or the second one? Like this? So this is a tensile strength test, right? It's a Brazilian test. If you remember what it was done a month ago or more, you will expect to have a tensile fracture which opens in this direction. So again, the same as before, you see you have to cut through layers of intact rock. And that's going to make it stronger. However, if you run the same test, but now you put the rock with the weak planes in this direction, you may expect that now this tensile strength is going to be much lower because the fractures are just going to propagate through those planes of weakness. So either for tensile strength or for shear strength, the orientation of the rock with respect to lamination and if there are planes of weakness is very important. And both shear strength and tensile strength are very important for wellbore stability as well, as we have seen in the equations, right? The equation of breakouts is basically shear failure. The equation of breakdown, it's basically tensile failure. So now let's take this to the context of wellbore stability. And let's say I have a layered sedimentary rock. It's not the same to drill a wellbore in this direction than drilling a wellbore in this direction, because the stresses that you're going to put around the wall of the wellbore are going to be at a different angle with respect to the lamination of the rock. And it will be a little bit more difficult to see exactly how the effect of that would be in these examples. But let's make a similar drawing, but with a little bit easier orientation to look at. Let's imagine a wellbore that we have a horizontal wellbore. And then we have a rock which is laminated, but it is dipping at a given angle like this. And those lamination planes are planes of weakness. And let's say that in this particular case, we have SH max. Let's say this wellbore is being drilled for hydraulic fracturing, so it's perpendicular, it's in the direction of SH min, and this is SV, and this is strike slip, and SH max is higher than SV. First, where would you expect the breakouts to happen? On the top and bottom or on the sides? Top and bottom, right? Everyone agrees with that? Okay, but now look at one more thing over here. Because of the orientation of the lamination of the rock, and because the orientation of the expected shear fractures in this rock, you will expect, if you remember, to have fractures in the wellbore of the wall if they are shear fractured at an angle. This is the same as running a test like this. And you expect to have fractures at an angle from this maximum stress. If you take the same thing, but now smaller over here, you will expect to have fractures that actually coincide with those planes of weakness. And same here and there. So now, if you have breakouts in that location, the rock is going to be much weaker at those locations because now you have the lamination of the rock exactly at the orientation in which you would expect to have shear fractures. So you will expect to have much bigger breakouts in these locations because the rock is much weaker than without the fractures. If you had the fractures at, or the lamination at this angle, the rock will be much stronger than here. So it's very important to consider that rock strength anisotropy, because otherwise, if you use an isotropic model, that's not going to work very well. Okay, so I think this is mostly it for all the Wellbore stability topics that we're going to see in this class. So any question about, conceptual questions about what we have seen so far? No? I already finished the exam, all right? I have to go through it again and check that everything is okay. But I can tell you, I can give you some hints and tell you that I expect that all these conceptual discussions that sometimes they do not go straight into the exam, they go into the questions, right? But they're very important. They're very important, and they have an application. And probably in the exam, you know, I'm going to throw you like some more real application problems than the ones that you may have seen in the homework. So I expect that you learn the fundamentals, and with those fundamentals, you are able to apply those to real problems. It's like, did you guys watch Karate Kid, old movie from the 80s? Did you? You see that, you know, like Mr. Miyagi just teaches basic stuff, and then after that, Daniel Sam is able to do all crazy things, applications into real life and real fights. Well, this is what I expect from you. I'm just showing you the basics, but I expect that you are able to apply these basics into and fundamentals into real problems. So let's go to the homework solution. And probably I'll come back later if you want to the fault homework solution, but let's talk first about Wellbore stability, since we just finished Wellbore stability. Okay, one thing. In Jeffrey's solution, I told him to fix this. He should have done it by now, but his problem 3A and 5 on stereonets, they were wrong, okay? So I also uploaded my own solution there, so you're going to have the two. Oh, this not for the homework, this is for the faults. All right, okay, let's see. The first problem is about computing stresses around a wellbore. I'm not going to ask you to use the Kirsch equations, which are very long, in order to compute stresses. But what you have to know conceptually here is what is the effect of each variable in changes the stresses around the wellbore. What is the effect of the orientation theta? This is an example with pressure in the wellbore, but similarly, you need to know what is the effect of the differential stress. You need to know what is the effect of the far field infinite stress. And all those three are going to have different effects on the stresses. So basically what you had to do here was for this particular problem, where SH max now it's coming in this direction, to calculate stresses around the wellbore, right? Remember, this angle theta is going to be always measured from the direction of the maximum principal stress. If we're considering vertical wellbore, the maximum stress we know is SH max, but if we were in a horizontal wellbore, it might not be SH max. It might be SV, it might be SH max. It could be either of those. So you have to look always at the plane perpendicular to the wellbore direction. And basically here, what I asked you to do was to compute this sigma theta theta, sigma RR, different orientations at 0. Probably you can't see very well the colors here, but probably now a little bit better. But these two are black, so this black, and this black, and this red, and this one is red. These black are for the case at let's see what is black here. At 0 degrees, and the red are for the case 90 degrees. The whole objective of this problem is just to see that the far field stresses are more or less the same after 1, 2, even 3, you could say 3 radii. Away from that, you see the far field stresses are just the same. The near wellbore stresses are the same as the far field stresses. So the wellbore doesn't have any influence at more than 3 radii from the wall of the wellbore. That's very important to know, because those variations are the ones caused by the wellbore, and they do not go very far. And conceptually, in this problem, what I was hoping that you get to see is that as you increase the effective stress radial support, what is the effective stress radial support in this case? 0, right? It's 0, and because of that, look, sigma RR is equal to 0 here at either at 0 degrees or at 90 degrees, it's equal to 0. But if we have some effective radial stress support now, let me keep the two plots in the same, so you can see both of them. Now your radial stresses start there. They do not start 0, they start there. Effective radial support in this case is 800 psi, and that's that point over there. Compared to the case before, also the hoop stress, before it was 7,000, now it is less, also because of the radial stress support. In both cases, after about 3 radii, the stresses are almost the same as in the far field. So the wellbore doesn't have much of an effect on further away from that. And if you were to plot more circles for that, you will see that this is the case with PW minus PP equal to 0. And this is the case with PW minus PP equal to 800. So by increasing the radial support, you decrease the size of the Mohr circle in this case. And that helps you reduce the likelihood of breakouts. You see how it gets further away from the shear line? Because now your radius, it's smaller. So in summary, it's very important to me that you know what is the effect of increasing effective radial stress support and changing the differential stress in the far field. And that's also reflected in the rest of the homework. Any questions about this problem? No? All right, okay, let's continue. The second one aims at looking at what is the effect of increasing pore pressure and how that affects the mud window. And in this case, we have a case onshore, and it's normal faulting. Okay, and it's actually the same case as in the notes what we solved in class. It's just an extension with looking at some other parameters. Here's the solution. I didn't write all the equations here because it would be just a repetition of what we have seen before. But if you want to look at the solution step by step of these problems, I recommend that you check my updated notes, and it's all in here. So, for example, let's see, shear failure. So you have the equations there, and here you have an example problem worked out from scratch. Okay. So I'm not showing this in the homework solution, but you can see that in the notes. So let me come back. So if you apply the equations for Wellbore stability, these are the results that you're going to get. Always, the most important thing is calculate well your in situ stresses. It's very important. I'm going to repeat this in the exam again. You need to know now about Wellbore stability. You need to know about fault stability, but you need to know how to calculate stresses and how to interpret stresses if you're given that data. So calculate stresses, then you know total depth. In this case, this is the vertical total stress, horizontal total stresses. This is the parameter of overpressure, so you can get the pore pressure. After that, very important, always calculate effective stresses. And given the rock properties, in this case, I recommend you calculate this parameter Q, for which you already have equations. And after that, you just need to put those equations into the equations of PWBO, PW shear, and PB, all the equations that we have seen so far. Remember also to use always the stresses in the plane perpendicular to the wellbore. In this case, this is a vertical wellbore, so we use sigma H max and sigma H min. If we were to have a horizontal wellbore, you will use the stresses that corresponds to the plane perpendicular to the axis of that wellbore. So then you input those values in there, and you can calculate what are the